Hi guys, welcome to week 2, day 2 from beautiful Big Bear, California. See, there's a tree behind me. We had some hail here earlier during the IS-50A lecture time. We're going to continue our discussion of Voroni. So there's all sorts of really interesting things you can do with the Voroni tessellation things. Your next assignment is going to be something called Lloyd's Relaxation. This isn't exactly what it looks like. So what you do is you start off with what you finished on Monday. So you start with a bunch of seed points, in our case cities, and you do a Voroni tessellation of it, and you end up getting something like that. And the downside to it is that you can get these really narrow, needle-like provinces like this, which it depends on your need. Like I said, Voroni is used in a lot of different contexts, but a lot of times, like if you're trying to make a random map for a civilization kind of game, it looks a little weird because countries normally don't have these really pencil-thin outlines. So what the Lloyd's relaxation is is after you finish the Voroni tessellation, what you do is you take the centroid of each region. Okay. So the centroid is the center of mass. So if you have ever done judo, you'll have heard the term center of mass before. If you want to throw somebody, you need to get under their center of mass. It's one of the most basic principles in judo is that you need, if you're going to throw them, their center of mass is going to be around here. Your center of mass is around here. If their center of mass is above your center of mass, you're going to be able to yoink them, right? So see, their center of mass is here, and so you load it up on your hip, and once they're there, you can toss them any number of different ways. It's getting there that's hard, And if you want to make somebody trip, people will trip once their center of mass is not above their feet anymore. That's one of the reasons why toes are important, and why feet are important. If all you had were these stilts, for legs, it's a lot harder to balance. If your center of mass ever extends out over over your feet, you're going to fall. Okay, and so the whole point of judo is to basically get their center of gravity, center of mass, away from their feet. And so you can do that by tripping them. I don't know exactly what's happening here, but you trip their leg, you pull their leg, here's a foot sweep. So if you do this, you move the leg out of the way and you move their center of gravity this way, they're going to fall. So that's the centroid right there. Okay, that's the centroid, and you can compute that in something like this by simply averaging together the row and the column for each city. So if you have this country here, you go through every tile that is owned by that country, you add together all the rows, you add together all the columns, and you divide by the size. That's it. And you got a new average row, you got a new average column, and that new average row and column is going to be the center point, the center mass. So if you were to cut out this shape here and put your finger underneath it, it would balance on it. That's the center mass. And so for every tile within this region here, you go through, you add up all the rows, you add up all the columns, and so you divide, not together, separately. So you add up all the rows and divide by the size, and that's the average row, right? That makes sense to you guys? To average something, you add up all the numbers and divide by the size, right? You used to perform juggling on stilts and jumping stilts, hard to balance, yeah. But that's cool. It's still cool you did that. So you do it this way, and then you do it this way. So you compute the average row, you compute the average column, and voila, that's your center of gravity. Then to do the relaxation, what you do is you move the city. So Constantinople will move. Moscow will move. So what you do is you move, because this is all done usually prior to the players seeing anything, right? You'll usually do a Voroni tessel. You'll create some random seeds, your Voroni tessellation, and then you'll run different cool things on it. Like I said, like I've seen algorithms where they'll make a river go down the thing and surround it with oceans if you're trying to do islands, and it's really useful for random map generation and many other things as well. And so if you want it to not have these kind of awkward looking things, what you do is you move the cities to that cross there, and then you rerun the Voroni relaxation, or the Voroni tessellation. Okay, so the point moves to here, and then you rerun it, and then if you want to do it again, you recompute the new centroid, the new center mass, the new center point, and you move them there, and then you can do it again, and then you can do it again, you can do it again, and eventually what happens is that they become evenly distributed across the 2D world. So if you do it too many times, you get a very boring map, right? Here's Kansas, here's Nebraska, here's Wyoming, whatever. Like in fact, in real life, they are kind of boring, like just rectangles, right? And so if you do the Lloyd's relaxation too many times, you end up you might as well just put the starting points evenly across the thing, and just call it a day. Kind of boring. And so typically, I might run it once, maybe twice. This is already kind of boring looking. This is maybe a little bit more interesting, like if you're doing like a real-time strategy game or something. And these are like the starting walls for the different players and stuff like that. This is a little bit more interesting than this. But if you want balanced, do this. I don't know. Or this is actually probably more balanced because nobody's in the middle like this person. So is that how they divided the states? No, they divided the states because nobody really knew. They're just like, take a ruler, that's Kansas. That's Oklahoma. And you can see where the natural boundaries are. Oklahoma, Indian territory originally. You can see when there's a river that's the natural dividing, because that's usually how they divide things up, right? The boundary between Oklahoma and Texas is this river. And so anytime you see a state boundary that follows this sort of meandering path like this, it's a river. And when the people doing the division have run out of ideas, it's a straight line. They take a ruler, it's at the 30th parallel. There you go. And so Canada and America's border is a straight line most of the way. And then over here, though, it gets interesting because the treaty between America and Canada said it runs between I don't remember the exact island, but it's like the boundary between Canada and America, let's say, runs between this island and this island. I think San Juan Island was one of them, and I think maybe one of these guys was the other one. But the question was, there's actually an island in between the two, and they didn't know about it, or maybe they knew about it but didn't care because it was too minor. So the international boundary was disputed between America and Canada because nobody knew who actually owned. I don't know if it's this island or which one, but nobody actually knew where. Like for here, it's pretty obvious the boundary is between here and here, and it's the midpoint in the channel, and that kind of goes most of the way. But I wonder if it was this one. Yeah, like it gets a little dicey. So it's a lot easier to just draw a straight line like this, most of the way across, and then you get over to here, and it jumps up like this, which is really funny. Then it jumps down, and then it goes this way, and then it's this really weird boundary. It goes through the Great Lakes. There's Detroit. There's Buffalo, and it goes up in a river there, and then back out a channel and a river, and then across. So yeah, if you're trying to make countries to look like real life countries, you have to think about: am I trying to make European countries, Asian countries, American states? Because they're, sometimes they follow natural geographical features, and sometimes they follow straight lines. And that's actually a valid question, right? Like, where's the boundary of Switzerland, right? If you're trying to make a random map. The Helvetican Confederacy, CH. Okay. And so you can see, like, it follows the waterways a little bit, but like if you look at this, you're like, what the hell is this, right? I don't see a river there. Well, let's switch it into satellite view. It's the top of the mountains. You see that? So the boundary between Italy and Switzerland is literally the top of the mountain range. So I was here in Zermatt 2 years ago, and if you ever get an opportunity to visit Switzerland, it's fantastic. It is one of my favorite countries on earth. And Zermatt's it's a pretty touristy resort town. Very beautiful though, nonetheless. And you can go up to the Gornergrat, where there's a train that actually takes you up here. And there's like glaciers and things like that, and there's an observatory, there's a hotel and a restaurant there, and you can go hiking around up here and stuff like that. It's pretty cool. And then over here is the Matterhorn, which is famous from Disneyland, right? And there is a chairlift that will take you up to where's the chairlift? Yeah, it doesn't matter. The point is, like, you can take the chairlift up there and you can literally walk over into Italy, because the boundary is the top of the mountain line. And so it's somewhere in here. You can't take a chairlift to the top of the Matterhorn, but it's like over here somewhere. And then you can just go walk around on the glaciers and cross over into Italy if you want, because natural boundaries follow rivers and mountains most commonly. So if you're trying to do that, then you can do some like simulations of like plate tectonics and things like that. And the low areas that are below sea level become rivers, the high areas become mountains, and you can do like an algorithm to find the highest point basically in a mountain range and have that be the boundary between your different countries, or the lowest point, the rivers, have that be a boundary as well. Or you can just simulate it using this, right, where you kind of scatter things out and then you pick the high points. Like, you'd have to make a lot of them, right? And you could pick the high points to form a mountain, and then you can put the boundaries of your country that way if you want. I like Wyoming's boundaries. Yeah, there you go. ruler, 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 ruler. There we go. It's done. If you're going to make a random map generator for the western U.S. states, it's pretty easy. Yeah. All right. So so your next homework assignment is going to be doing the Lloyd's relaxation. So basically, take the centroid, move the city there, rinse and repeat as many times as the user wants. So I can show you what this will look like. This should be fairly easy. I don't know if I added any spiciness to it. Let's see. CD Voroni to Vim readme. Use the working code for your Voroni tessellation. Follow it up with a Voroni relaxation, Lloyd's algorithm, and a Voroni iteration. You average X and Y coordinate for each space, centerpoint, and then you run it again. Yeah, that's it. So it's pretty easy, honestly. It's probably about 6 or 7 lines of code total. I give you a working implementation here. So, we're going to do that reference. But you can use your own. In fact, I would even almost suggest you use your own instead. So here we have a randomly generated map. You see we have a lot of these like really weird looking countries like this. And so do you wish to do a Voroni relaxation? Yes. And so what's going to happen is that this E here is going to move down to its centroid, which is going to be around here somewhere. D is probably going to move right a little bit. J is probably going to move down to here. M is probably going to move to here. C is going to move to here. And then after you've moved the cities, you rerun the tessellation again. Okay, so you see that E did move down, like I said. C moved to the right, and then you rerun the tessellation. And then you can do that as many times as you want. Let's see here. K is probably going to come down this way a little bit. Yep, right where my mouse was. Cool. And things turn more round. Like you can see, G is almost a round country now. And if you keep running it, then the points will sort of evenly distribute themselves. You end up with the Colorado-Wyoming boundary. Like this is basically, yeah. This is what happens when you relax too much. It's what happens when the people doing the partitions. We could go out there and see if there's like a mountain or something, or a river, or like an island that nobody knows about, but nah, yeah, whatever. Line, done. Yeah, it's like fence posts almost, yeah. Okay, so that's your assignment. And same as before, just screenshot it and post it on Canvas. Do you guys all understand what you need to do? After you've finished all your calculations, if they do a Voroni relaxation, if they say no, you just quit, right? It's like if they say no, that it's the same as Voroni 1. But if they say yes, then you move each country, each city to its center point. You rerun Voroni, rinse and repeat. That's it. It's I can actually tell you how many lines of code mine is. Move it off here, then CC, relax. Lloyd. It's a little bit more than, okay. It is, 20 lines ago. Because I have to delete the old content, make the new center point have the content, do the averaging. So about, yeah, you could probably do it faster if you're, like, I have comments in there and stuff. Yeah, Walker's is 4 or 5 lines. Yeah, you could probably do it in around 6 if you wanted to, but I have comments and stuff too. Okay. Else die. No, actually, when you quit, you have to print whoever is the biggest country still. So you guys got one day to do this. That's it's a cool little algorithm, and like you saw on that website that I had open a second ago. Like, there's all sorts of like cool things you do with it. This kind of looks almost like a tree or something like that. And so this is doing a Voroni, and then Voroniing the Voroni, and sort of going into, instead of doing a Lloyd, it kind of goes inside of the Voroni region, and then scatters more seeds and partitions it and things like that. Yeah, so this would be a Voroni tessellation of, oh, that's cool. Look at that, it's animated. That's really neat. I like that, on a globe. Huh. Neat. If you were to run Voroni on the capitals of America, this is what our states would look like. It's pretty cool. I mean, it's cursed, but it's pretty cool. So, Texas, Michigan is the same, is it? Yeah, look at that. pretty cool. I like that. Hold capitals. Poor Russia. What is that? Who are you? Okay, yeah, so it's all sorts of fun. Let's see. Okay, so what was the other thing I was going to talk about today? Fresno's in Nevada, yeah. What was the other thing? You're back, awesome. Find the center, then move. Yeah, I mean that's what we just talked about. That's your assignment. But there was some other topic that I was going to talk about. You wanted a summary of best hits from 45 or something. Edge detection. Yeah, edge detection is the next one after that, and that's useful for doing things like making those mountain ridges and things like that too. Edge detection is actually pretty useful in a lot of contexts. Like if you're doing image recognition, computer vision, like you're trying to make, if you're going to go to work for Tesla and work for on autonomous vehicles, edge detection shows up a lot there. It's very similar to how human vision works. Human vision, there's a chunk of our brain in the visual cortex that detects edges. Like that yellow stripe at the top of the screen, I don't know if you guys can see it. The black stripe here. Like the human vision calls out edges, and that helps us form shapes, which helps us identify objects and things like that. Raycasting. Talk about raycasting. Yeah, we can actually do that. Let's do that. Okay, so one note. So IS50B. That's right. I've been meaning to talk to you guys about the. It's not logged in. Sign in. Do I remember my password? I don't. No, I don't remember. Sorry. Okay. Okay, so today we'll talk about data structures for Vidya. So there's a couple operations you're going to do over and over again in a video game, a 3D video game especially. 2D video games are a lot easier. I guess we can talk about 2D really fast. You've got Mario, right? You can represent Mario as a rectangle or a square. And you've got a box, right? Gold. Do. Maybe not you, whatever. You get a box. And so Mario jumps. So every frame of a game, you are going to be type, lasso, select, panning hand. Can I just click on you? Yeah. So every frame, let's say Mario is running to the right. Can I drag you? Yeah. Mario is running to the right. He's got a velocity. He's got a horizontal velocity, and he moves that far every frame. Okay, it's like maybe he'll move that far in one frame, and so you need to know if he runs into something. And so in a Mario style side scroller, it's really easy because you've got boxes and things like that. And if your new position is going to intersect the position of an obstacle. It could be a block, it could be a Goomba, a question block, whatever. Then you need to handle the collision. So collision and tracing are like the two big things we need data structures for. Make the font a little bit bigger. Okay. Okay, so these are the two big things that we need to accelerate when doing video games. And collision detection, like I said, it's very easy for 2D because typically things are just rectangles. And to tell if a rectangle overlaps another rectangle involves a couple if statements, right? If, you know, my max x is between your min x and max x, and my min y is between your min y and max y, congratulations, they're overlapping. And you can actually do it even faster than that using the powers of algebra. Like you subtract out the top left corners, and you can optimize it pretty quickly to see if a rectangle overlaps a rectangle. Hash tables, and hash tables. Yeah, actually not so much for this, right? If you're talking about landscapes and things like that, yeah, like big scale stuff is typically hashed. You have giant buckets that hold all the objects, but for tracing, I mean, I guess hash tables could give you some good speed up, but there's some other approaches as well. So collision detection in 2D, you guys are thinking this is called a axis-aligned bounding box. Axis-aligned bounding box. Is super easy, right? Even in 3D. So if you have, in 3D, it's just, you know, is my min x between your min x and max x, right? You just add one more check in there. So let's move Mario and our question block over here a little bit, get out of the way. So do you guys understand that? Like you could probably write, like I think I've done it even in CSI 40, like, you know, true or false, do these two rectangles intersect? It's pretty straightforward. Triangles are a little different. So how would you do this with a triangle? You got a triangle, and you got another triangle. How can you tell if they overlap or not? To make it more complicated, point doesn't need to be on the inside. In 3D? Nah, this is stock 2D. This is stock 2D. How'd you do that? Comparing each point, yeah, that would be painfully slow. Yeah, you could rasterize. Rasterizing means you go through all the points inside of a triangle and put a pixel value on the screen. You can see if the two of them overlap on the same location on the screen. Yeah, that's if you're just trying to see if two things touch. Like if you're making a video game and you want to see if two things are intersecting each other, you don't want to do that. Like rasterization is kind of an expensive step. You don't want to do it willy-nilly, right? So a couple different ways of doing this. I think the easiest way from like, 7th grade, 8th grade algebra is you can just do a line intersection test, right? Like, does this line segment intersect with that line segment? Does it intersect with that one? Does it intersect with, you know what I mean? So, that's one way you can do it. That might be a little bit expensive. So the first thing you might do actually is you might actually, like, what if it's like way over here? You can actually, you see how there's a bounding box around this thing here? And there's a bounding box around this one. You can actually start off, you can start with an axis aligned bounding box check, right? Hey, my max y is smaller than your min y. False. They don't touch. You know what I mean? My minimum, is bigger than your maximum. They don't touch. Easy, right? But let's say the bounding boxes do overlap, like that, right? The bounding boxes do overlap. Then you're going to need to see if the line segments touch. And so a simple way, is to do a line segment intersect test. You guys remember that from algebra? Y equals mx plus b. You guys remember that? Solve for y, right? Getting flashbacks, yeah. And so basically what you can do is you can just basically compute where, because this line is a slope, and you can compute where this line would hit this line. And if that intersection point is on both lines within the minimum and maximum, then they intersect. Another way of doing it is you could project you can do what's called a projection, and project one line onto another, and that is like a cosine, I believe. And so there's faster ways of doing that too. And so you would like project this line segment here onto the thing here, and it'd show you, it's like a shadow. Like if you get a flashlight and shine a shadow onto something, that's a projection. You're projecting a shadow onto something. You can do that and see within that distance there if it is going to hit, things like that. But I don't know. Don't need to worry about that too much, because the thing is, like, if you start with an axis aligned bounding box, that's actually going to throw away most possible collisions. If I've got a water bottle here and a water bottle here, their axis aligned bounding boxes aren't touching each other, and then you can afford to do the more expensive collision tests when, if and only if they touch, right? So things get a little bit more complicated if you allow rotations. Can I rotate? There we go. There we go. So if you allow rotations, then it gets a little more complicated, and you have to, you can unrotate it, so you can make it an axis aligned bounding box essentially. But then you're getting to the thing where, like, all right, well, does this line segment cross any of the four? You can always rotate it, like if they're both rotated, you can actually rotate them. You can rotate at least one of them to be axis aligned to make the tests easier. So in this case, like, that one is axis aligned. Axis aligned means that it's straight up and down. It's on the x and the y axis in this case. So so you could do a line intersection test here and stuff like that. Here and here and here and here. Four of these tests. Like I said, there's faster ways of doing it too, but that's at least a straightforward way of testing it. Now it gets more complicated. So let's say we've got a multi-line. Can I draw a multi-line? Single arrow, no arrow. I should click on this every time I draw a line segment. Good enough. Okay. So this is something called a convex hole. Okay. So type. Start with something easy. So what is a convex hole? What is the definition of a convex hole? A convex hole is any polygon in which there are no acute angles. Depends on which way you look at it. A simple way of defining it is for any point inside of the convex hole. I'm trying to draw a circle here. Can you see all of the points inside of it? So no matter where I stand within this convex hole, I can see all of the vertices. Okay. Something that would not be a convex hole would have like let's say you had like a back, like let's say the thing came out like that. Then if I was standing here, I would not be able to see that point back there. Okay. But if you were standing here, you could probably see everything. But you have to be able to see every vertex from every point within the convex hole. So from that point, I can see all 5 of the vertices. That makes something a convex hole for every point. Okay. So 4 sides or more, doesn't need to be. A triangle is a convex hole. Right? Because for any point inside of the triangle, I can see each of the vertices. I've got line of sight. Doesn't cross any lines. Okay. So a convex hole is kind of like a polygon, but with restrictions. So it doesn't have any it doesn't have any acute angles, like I said. Like, ignore this part right here. Right. So it doesn't have any things like that. Okay. Where the thing bends at more than 180 degrees. Or obtuse. I don't know. Whatever. It depends on your perspective. It's acute from this side. It's obtuse from that side. So for the lake you made, how did I adjust the plan? I changed the scaling to be 40 times in each direction, and then I used the translate tool to just move it up and down until I found a good spot for it. So, Biddinghoven, does this make sense to you? This is not a convex hole, but this is. Okay. So, let's say that somebody gave you a non-convex hole. There's actually a theorem that says you can take any non-convex hole and split it into convex holes. So in this case, that line there is actually perfect. You can see that I could split this non-convex hole into this triangle up here and this convex hole up here and this convex hole down here. So no matter which set of points you're given, you can always split them into convex holes. And this is very common in 3D games because most algorithms that we work with in gaming require convex holes. And so if there was like another, I don't know, area back here, then the map tool, like the game developers make, would split this part off into its own convex hole. It'll split this part off into its own convex hole. And it'll probably have a data structure saying there's three rooms on this map, room A, room B, room C. But the person who made the map doesn't even need to know that. They just kind of sit there and go, bloop, 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 I'm just making a cool map, you know, I'm just making a cool map. And then the map tool itself is going to be like, all right, we're going to segment that off, we're going to segment that off. There's a little bit down there, and then here. And then the map tool itself will create convex holes because pretty much all of our algorithms require convex holes to work. But it's not like I said, it's not a big deal because if somebody gives you a non-convex hole, you just split it and you run the algorithm on both of them. Okay, so to adjust the plane to look much steeper, right? Like a deep end. Rotate it. Use the rotate tool on it. You should be able to rotate it up like that. So yeah, okay, so we got a convex hole here. So does a convex hole include a point? So let's say I'm gonna take a different color here and say this point right here. Is this point within the convex hole? How do we figure that out? How do we determine that? And this is a common operation, but like I said, a lot of in this same principle applies in 3D as well. You've got a lake of lava, right? And the player has fallen into the lake, and you want to know if the point they're touching is lava, or if it's water, or if it's slime, or if it's air, or if it's solid. This is called a point contents check, and it's called a point contents check. Very common thing to do. The bullet just hit something. Did it hit a person? Did it hit lava? Did it hit water? Did it hit a wall? What did we hit? What is at that point in the world? Okay. So, how do we tell? How do we tell if this point here, like let's say the map maker went and they put a lake of lava in there, and the player dropped a grenade. The grenade falls into the lava. You need to see if the point that the grenade's at is lava or not. If it's lava, it detonates or something, right? How do you do that? How do you tell if a given point, is within a hole or not? Shoot a ray below their torso and see what it hits. Yeah, but we don't have tracing yet. We haven't gone to tracing yet. It's talking about point contents. It's even simpler than tracing, right? So how do we do it? Do you guys remember the basic building blocks of game math and stuff? You got your cross product, which tells you if something is right or left. You got your dot product, which tells you if something is pointing the same way or the opposite way. And I can make this field bigger, maybe. Okay. And so usually when we do a convex hole, usually we specify in our engine that all of the points in it are going to be in clockwise order or counterclockwise order. Doesn't matter which, you just have to be consistent. So if you have a data structure holding the convex hole, one of them arbitrarily is going to be point number 1. It doesn't matter. Like maybe this guy's point number 1. And then this guy would be point number 2. This guy would be point number 3, point number 4, and point number 5. They have to be listed in clockwise order for these algorithms to work. So, what we can do is, how do we tell if this point here is to the right of every one of the vectors, then it's inside of the convex hole. You guys see that? So if that point there is to the right of 1, 2, if it's to the right of 2, 3, if it's to the right of 3, 4, if it's to the right of 4, 5, and the right of 5, 1, if it's to the right of all of them, then it's enclosed within it. Okay? So which one do we use? Do we use cross product or do we use dot product to do that? Cross product, yeah. So what you do is you take this point and you actually make a vector pointing at it. That's a terrible vector, it's a curved line. You make a vector pointing at it from one. I missed my tablet. There we go. Okay, so you make a vector pointing from 1 to the dot, and you have your 1 to 2. You cross product them, and it will tell you, is this guy to the right or is it to the left? And yeah, that's it. So, is it positive or negative? It just depends which one you do first. If you do the 1 to 2 first, then I think the answer is going to be negative, and if you do it the other way, it'll be positive. It doesn't matter. You basically just do the cross product and just be consistent which one is first and which one's second, and then you say if all the answers are negative or if all the answers are positive, again, just depending on which one is first. Then if they all are, if they're all to the right, congratulations, it's inside. If any of them are not, like for example, this point here is to the right of 1, 2, it's to the right of 2, 3, it's to the right of 4, 5, it's to the right of 5, 1. It is not to the right of 3, 4. So if any of them, it's to the left of it, it's outside. Okay. Is there a way to import packages from other projects into a new project? Yeah, copy the folder over. Yeah. It'll break if they're referring to things, like if you've got blueprints that are referring to other things. That's one of the reasons why I put all of my stuff into the build directory, so I can just copy that over if I need to. So it's not referring to other things. Starter content, I guess. These products return in a range of -1 to 1. Yeah. They don't have to, but it's common for you to normalize them first. So if you've got a vector of length 5 and a vector of length 5, you normalize them down to be vectors of length 1, and then you normalize, then you cross product them. So you get a size 1 answer. You technically don't need to normalize them, I guess, for cross product. If you get a negative number, it's to the left, it's to the right. If you get a positive number, it's to the left. So you technically don't need to go to that step. But typically, yeah, we just normalize and get a number from -1 to +1. So again, whether -1 is left or right just depends on which one you do first. It makes very little difference in the bigger scheme of things. I have some experience with this using vector 3. Yeah, it's pretty common for people to make their own vector 3 class and make a cross product and a dot product and all that kind of stuff. Do they intersect? Yeah, vector 3 is found everywhere. Yeah. Okay, so yeah. So if you're given a point and a convex hole, it's fairly straightforward to determine if a point is inside of it or not. But how do you know which convex hole? Right? How do you find the convex hole? Well, that's a story for another time. There's a number of ways you can hold convex holes in your map format. When the game's running, how do you hold all the different things? So like when somebody's building a level, they're going to be doing things like a map maker is doing things like this. Like they're going to make a river, and they're going to draw like some hillsides. This is really bad, but they'll put some water in here. And this is mountain. That great artwork. And so then they make this in like a map maker, or they make it in like Unreal Engine or something. And this needs to be saved in a format that allows you to recreate it when the game launches, but also that hopefully the game engine doesn't have to do a lot of intensive visibility computations and things like that during the game, because that'll tank your frame rate. So these things will oftentimes be stored in different ways, and you can store them in a convex hole and a convex hole and a convex hole. And then there's some sort of data structure, which I haven't talked about yet, that if the user says, okay, tell me if this is water or not, then it will very quickly in log base 2n time tell you, okay, that's the river convex hole. And then then you can do a point content test to see if that point is within the boundary of the river. And 2D, 3D, like I said, it's actually the same thing. You just have to do you take the normal of the plane, like if it's a 3D object, like imagine it's a cube or something, and you want to see if a point is inside of a cube, you can take the normal vector of each of the faces of the cube and see if it's inside, right? So same general idea. All right. Yeah. All right. Yeah. And so if two convex holes intersect, then that's not convex. Whatever. It's fixed. It's very hard to draw a convex hole when your mouse puts little backwards curves in it. Whatever. You get the idea. So do two convex holes intersect? Again, the first thing that I would do is do a axis align bounding box check. When you make your convex hole, you can actually do you can actually figure out what's the minimum, what's the maximum, like that. You see that? Make it white. No. Make it white to stand out a little bit. Line it up again. There you go. So when you make your convex hole, you've got a set of points. If you're storing a convex hole in like C++, you can literally just store it as point, like a vector of points, or an array or whatever. And then after you do that, when you process your convex hull, you can figure out what's my minimum x, what's my maximum x, what's my minimum y, what's my maximum y. And then if you want to see if two convex hulls intersect, then basically you start off by doing an AABB check, right? You just see, are they anywhere near each other? And if they are, then you basically do the same kind of thing here, where you can do a line intersection test.
Dad, would you like some water?
I got 2 bottles of water, but thank you. Yeah. So you could see if any of the points are inside of each other. I think that would work also. Let's see. Can they overlap? Yeah, they can overlap without necessarily one of the points being inside of the other one. So, yeah. Yep. And so in general, we try to avoid actually doing, because this is going to be annoying, right? Because like you're going to go through all these line segments and maybe find out which one's closest or something to cut down on the complexity, but you're basically doing a whole bunch of line intersection tests. And yeah, that can be expensive. And so very commonly when we have collision detection in video games, it's just the AABB. Like it's fairly common to just not have any sort of accurate collision at all, and just call it a day. You know, but yeah, sometimes you're shooting a gun at a convex hole. You need to know if you hit it or not. So that's what you got to do. What you got to do sometimes. For players, oftentimes a player is represented using a cylinder. Let's see if I can draw this using my powers of middle school art. Yeah, there you go, cylinder. Okay, and so it'll draw as like some doom soldier or something, right? Like here's the doom soldier. But in reality, it's a cylinder. And sometimes they don't use cylinders; they use capsules, which are rounded, like a pill, like a rounded cylinder, kind of like bullet shaped at both ends. And they do that because the head kind of it better matches the head of a person. But either way, like you can have these issues where like you can shoot somebody like here, and it hits the cylinder or it hits the capsule, and there's no body part there, but you shoot underneath the chin. You miss the neck, but it'll still hit the person because, like I said, in video games we care about speed. Sea of Thieves use the capsules. Sure, Minecraft an easy time dealing with collision if everything's on a grid. A bean, yeah, it's like depending on the bean, but yeah, like a pill, like a rounded, a cylinder where the ends are rounded. Yeah, kind of looks like this, and then the head would be here, something like that. But even still, there's going to be areas like underneath the chin, underneath the neck, where you'll get a false hit, right? And a lot of times, this doesn't matter, right? Like if you get hit, you don't know that they were actually aiming here, right? You just know they were pointing the gun in your direction and you got hit, whatever. The only time I've seen it actually like matter is like when you have a laser dot, and so you're projecting the dot onto a person. And if you're using the capsule or the cylinder, then the dot will float in the air over their shoulder, and you release and they explode. And you know that you missed them, So with like laser sights and things like that, it can be humorous. And the answer that a lot of people give is just, I don't care. You know, both for game developers and for players. Like, I don't care. You know, in the greater scheme of things, it's much more important to have frame rate. But if you need to, then an Unreal Engine has this option. You can choose to either do coarse grained collision, or you can do both coarse and fine grained. And so if you try shooting here, and it hits the cylinder, this is a very easy test too, because this is an axis aligned cylinder, right? From a top down perspective, it looks like this, right? You know, to tell if a point is inside of a circle is super easy. Do you guys know how to do that? Here's the center. Here's the radius. Here's the distance to x, d. If d is less than r, it hits. Right? If the distance to x is smaller than the radius, it's inside a circle. That's all it is. And you can compute the distance using a Pythagorean theorem, right? It's square root of x1 minus x2. Right. And so to compute if x is inside of a circle, in 2D especially, it's really easy. You know what the radius and you know what the center of the circle is. You compute the distance from the center to x, and you see if that distance is smaller than the radius. Do you guys understand? Like, you got the radius here. If the distance to x is smaller than the radius, you're inside the circle. It's like easy. It's real easy. Easy to code. You are involving a square root, but here's the thing, you don't actually need to use a square root. So for this, I actually would not use the hypot function, because, check it out, the distance to x is equal to the square root of x quantity x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Yeah? Does that look familiar to you guys? Pythagorean theorem? Right? Yeah. Good question. Is it less than or equal to, or is it less than? Doesn't matter. When you're working with floating point numbers, it's very, very rare that the two of them, especially after you're doing squares and square roots, even if they're the same number, they're probably going to not be the same number. It's floating point error is weird like that. Yeah, if you want, make it less than or equal to. Sure. It's all good. Now, so what you can do is you can compare. You could say if I don't want caps. Thank you. If the distance is less than or equal to, no, distance is equal to this. Right. Sorry. If distance, that's the hypot function, right? So the distance to x is computed with that. So if the distance to x is less than or equal to the radius of the circle, then it hit. Otherwise, miss. You guys, nothing on this? Like, this is a very, very simple way of telling if something's inside a circle. You've got the x and y position of x. You've got the x and y position of, I shouldn't call it x, huh? Oh, of C, the center. Okay. Now, as it turns out, you actually don't need to do the square root. Watch. Delete the square root.
I bought it from. Well, you bought it from you because they say that I'm the best.
Yeah, see that?
I'm the best pet area. Yeah, anyway,
And you don't even need to save the radius as the radius. You can actually save the radius. A lot of times the radius is saved as the radius. And then they also save radius 2. And if you've ever seen radius 2 in video game logic, it's the square of the radius. And this is why they do it. So that you don't have to keep squaring the radius every time you do a computation. You just save the square, and then at any time you need the square of the radius, you just use that. And so to do a hit detection here, it's 2 subtractions, 2 multiplies, and squaring something. Yeah, it's not that expensive. So 2 subtracts, 2 multiplies, and an add, and then a comparison against a number. So that's pretty darn fast, right? And then for a cylinder, it's the same thing, except you get rid of the z-axis. You just basically say, hey, is the hits z in between my max z and my min z? We don't allow tilted cylinders. This is an axis-aligned cylinder. Okay. This is an axis-aligned cylinder. AC. And so we don't allow this. We don't allow people to lean forward in our video games, right? Or lean back, or we do, but like not if we're doing this. And so if you allowed people to lean forward, their head would actually stick out of the cylinder because the cylinder doesn't tilt. And so if you want to see if the point X here is in the cylinder, you first be like, all right, is it between here and here? Z max, trying to write with a mouse, Z min. There you go. So is its Z value, between these two values? Yes? Okay, cool. Now we'll do this. And that's it. It's a really easy check. Okay. So that's why we use cylinders and capsules. Capsules are cylinders that have a half sphere on each side. Sphere intersections are very easy as well, right? It's the same as a circle. Is the distance to the point within the radius of the sphere? Yes, it's a hit. So sphere detection, sphere hit detection, cylinder hit detection, cube hit detection. These are all really, really easy things. And that's why you will see those be the fundamental building block of most collision detection systems, simply because they're easy to code, they're fast to do. The downside is you don't get good precision like this, but if you really want to, you can then be like, all right, it hit the cylinder, let's now test this. And there's ways of speeding that up too. So it's like a log base 2n to find the nearest point or the nearest triangle, and then do a test on that if you want. Further from center axis, less damage. Not necessarily, because if you headshot somebody here, like that's usually double damage or something, right? Yeah, like a lot of times the Z component is actually used to crit people, right? So after you hit somebody, you can get the Z component out, and you can see if you say. So you say. So let's say we know that x.z is between z min and z max. We could say x.z, it's too small, x.z minus z min. That is how high it is above the minimum. We divide that quantity by z max minus z min, and that will give us a fraction of how high up the body we hit. You guys see that? So like if x.z was like halfway between z min and z max, then you're going to be hitting the torso. If the number is like below 0.2 or something like that, then it's a leg shot. And if it's like above 0.7 or 0.8, it's a head shot. Okay. And so the result of this little bit of algebra here, you can be like, all right, if the number is above 0.8, double damage, head shot. If it's below 0.2, half damage, leg shot, but reduce their speed. Otherwise, regular damage. And that's a fairly common thing to do. Very easy calculation. Very easy calculation to do. So, yeah, but as far as like, you could probably, like if you really wanted to, if you really didn't want it to hit the space between the neck and the jaw and the shoulder, you could probably add some simple tests, like if that result is here and it's this far, I don't know. Like I said, like most of the time people just don't care about it. Like gamers have gotten accustomed to just hitboxes being hitboxes. You know what I mean? You shoot at this guy over here, hit. Like we're just unless it really matters for the game. Like if you're trying to figure out if you're in a pool of boiling lava, yeah, it absolutely matters, and you need to do the convex hole, test. But for like a lot of things, we just bounding box it and just accept the fact that, yeah, it's gonna suck. All right, so it's 3:45, so that should be good for today. So we will pick up this perhaps tomorrow. Convex hole include a point. Triangles touch. Before we do that, let's and circles. So do 2 circles touch. We can talk about that tomorrow. It's pretty easy. Do 2 circles tomorrow. Do 2 circles touch. Does a circle or sphere? It's just as easy. Include a point. Does convex hole include a point? Do 2 convex holes overlap? Yeah. So yeah, we'll just call it there. So you guys got your Voroni 2 to do. That'll be due tomorrow, and we will continue our discussion of like kind of the secret mechanics behind video games and the computer science that enables it to run quickly. Nobody wants to play a game that runs at 7 frames a second. You know what I mean? So, all you have to do is Lloyd relaxation for tonight. Find the center, move the city, and then rerun the Voroni. That's it. Don't forget to rerun the Voroni. If you move the center and the things, you got to move the center, then rerun the Voroni, and it'll change the shape of all of the countries or city states or whatever you call it. Reprint? Okay. Yep. And then reprint it. Yeah. Yep. I am teaching CSI 1 at Fresno State in the fall. Okay, that's it for today, guys. Simmons and Aaron, I will hang out for a little bit. If you guys have been here in the chat channel patiently waiting, so if you guys have any questions about the lab time right now, fire away. I'm going to go ahead and stop the recording now. See you guys tomorrow.